Okay, and for the last problem on the multiple choice, we have number 11, and for this one, we need to do a polar coordinates area integral. So we have two curves. We have R1 is square root of 2 sine theta, and we have that R2 is equal to 1. So we want the area inside R1 and outside R2. So we definitely are going to have to graph this. So R2 is a circle with radius 1. That's all it is. And R1 is a constant times sine theta. So remember, if you have R equals some number times sine or cosine theta, you get a circle, but you just get one that does not have the center or the origin as its center. Instead, it has the origin as an edge. And since this is sine, this number is positive. We know this circle takes place directly above the origin. And it has a maximum point there of square root of 2. So this looks something like that. So we want the area that's inside this graph but outside this graph, so we're talking about this area right there. So what we need to find are these intersection points. So we need to know, where does root 2 sine theta equal 1? Where do these r's equal? Well, that happens when sine theta is equal to 1 over square root of 2, in other words, square root of 2 over 2. And where sine theta equals square root of 2 over 2, that is when theta is equal to pi over 4, or 3 pi over 4. So this point right here, so this point has r of 1, and we have pi over 4. And this point right here has r of 1, 3 pi over 4. We know those must have r of 1 because they lie on this circle. So we need to now integrate to capture that entire area. So remember that for finding the area of a section of a circle or some other polar graph, we're essentially using the formula A equals 1/2 r squared theta. So that gives you the area of a circular section. And remember, in polar coordinates, like how in Cartesian, when we do an integral, we're making very, very, very small rectangles. In polar coordinates, we're making very small circular sections. So we're going to integrate over theta, just how, like in Cartesian coordinates, we integrate over x. So if we want this area, we have 1/2. We need to integrate r squared d theta. So what is r squared? In this case, it's going to be the outer one squared minus the inner one squared. So we have, in this case, r1 squared minus r2 squared d theta. So now, and we're going from, in this case, pi over 4 to 3 pi over 4. However, there is a little bit easier way to do this. Because these are circles and you know this is symmetric, we could just stop at pi over 2, get the area of this part, and just double it, because you know it has to be the same. So let's do that instead. So instead, our area is going to be 2 times 1/2. The integral, instead of going from pi over 4 to 3 pi over 4, let's go from pi over 4 to pi over 2, since we're doubling it there. Pi over 4 to pi over 2. And r1 squared, well, we just take this and square it. If you square root 2 sine theta, you would get 2 sine squared theta. And r2 squared is just 1. And in front here, these 2 and 1/2 cancel out. So your final integral that would give you the area that we're talking about here is this. So we would be integrating 2 sine squared theta minus 1, and we would be going from pi over 4 to pi over 2. So keep in mind, if you had not done the cut it in half and double it strategy, you would have just had half the integral from pi over 4 to 3 pi over 4. But on a multiple choice exam, or if this is a multiple choice problem, obviously you couldn't have both of those answers there because they're both right. So you need to be able to, you need to be flexible in being able to switch back and forth, because in this case, the only one of those that's actually on here is the one that we ended up with, which was using the half and doublet strategy. So you need to be okay with using symmetry, just because you can get multiple correct answers on these types of problems depending on which way you did it, and the way that you did it might not necessarily be the multiple choice answer that's there. So being able to do this symmetry strategy is pretty important.